We're going to talk about what's known as the epsilon delta definition of a limit. And Cauchy, a French mathematician, came up with this about 100 years after Newton and Leibniz first came up with the idea of calculus. So it's not something that we have to know and understand. Clearly, Newton and Leibniz knew what they were talking about, and they didn't have this very rigorous and precise definition that Cauchy came up with later. And this will not be tested on the AP exam, but we're going to talk about it so that you can kind of have some exposure to it. And maybe for some, it will enrich and maybe clarify your understanding of limits. If not, don't worry too much about it. This is not, you don't have to have mastered this to be able to have great success in the rest of this class. So the idea is, we have said that our understanding of a limit is that, which is good and will suit us well, is that as x gets closer and closer to c, then the y values are going to get closer and closer to L. So here's the x value of c, and whether or not the function is defined at that point or not, we know doesn't matter in terms of the limit. Okay, so it might be undefined or it might be defined to be something else, and the limit could still exist. So we're going to write it down something like this. So here's going to be our epsilon delta definition. I guess I should say maybe first, as an aside, we need some vocabulary and symbolism. This is going to be the symbol for epsilon, which is a Greek letter, and this kind of like an S that comes around and loops up is going to be a delta. So those are the symbols that I'm going to use for those Greek letters epsilon and delta. So we're saying that the limit as x approaches c of f of x equals L. So for that to be true, for that limit to exist and be equal to L, we're going to say let f of x be a function. So f of x be a function defined on an open interval containing c. So the interval contains c, and then I'm going to say in parentheses except, so the function may not be defined at c, so except possibly at c. So the function is defined on the interval which contains c, but the function may or may not be defined at c. And then we're going to say let capital L be a real number. Okay, so our limit, so the limit, whoops, I don't want a capital L, the limit as x approaches c of f of x equals L means, and I'll try to clarify this because I'm sure it's going to be confusing, for every epsilon greater than 0, there exists a delta also greater than 0, such that c minus, so for x between c minus delta and c plus delta, then I'm going to come down here, then L minus epsilon is less than f of x, which is less than L plus epsilon. Or the way we will more often see it is going to be with absolute values. So the absolute value of x minus c, let me back at that, I'm going to say 4. For the absolute value of x minus c less than delta, the absolute value of f of x minus L is less than epsilon. Okay, let's see if we can talk about what this means. So it kind of works the way that it's like a call and response, or we say, okay, I think the limit of this function f of x is L as x approaches c. So if that is true, then for whatever value of epsilon you pick, so you might say, epsilon is going to be maybe 0.5. So this is the hypothetical. You say that you want all of the function values to be within 0.5 of L. And then I say, okay, for that particular choice of epsilon, then I can come down here and say, here's where I'm going to choose my delta. So delta is this distance when you choose your epsilon to be that distance. So you pick the epsilon, then I come up with the delta, and then my claim is then that all of the values of x in this interval within delta of c that you plug into the function, we are going to get y values that are within that epsilon of L. Now you may say, I'm going to change my mind, and that's fine. I want epsilon to be, let me do something other than blue because I've already done that. So we're going to choose epsilon to be, you say, 0.1. And I say, that's fine, but since you picked a new epsilon, then I get to pick a new delta. So now you're saying you want all of the y values to be much closer. Now this is your new epsilon right here. So that's the new choice of epsilon. So then I'm going to say, okay, then I'm going to pick for that epsilon, I'm going to pick the delta to be there. And if I can find a delta for your choice of epsilon, so that all of the values of the function will fall within that interval, within that range of L, if I can do that for every choice of epsilon that you can come up with, then we say the limit does in fact exist and is equal to L. Okay, so what it rules out, let's just talk about kind of the theory of it. So suppose we had a function where the limit didn't exist. So maybe it could be one of those three ways we know that the limit can fail to exist. Could be that the left-hand limit is not equal to the right-hand limit, or it could be that it goes to infinity, or it could be that crazy oscillation thing. So if this is our c, this is what we want the limit as x approaches c equal to L, then now we have kind of a tough choice. What are we going to call L? Do we think this is our value that this is approaching the limit? Do we think it's this one? Are we going to pick a number halfway in between? So you can see already this might be a little bit tricky to pick. So the fact is it won't matter because it's not going to work. Because if you choose an epsilon that's like smaller than that, so suppose you choose an epsilon, suppose and whatever L we pick, suppose we pick this as our limit. We think that the limit as x approaches c of this function f of x is going to be that L2. So here's our function right there. Well, you can see that if we just pick an epsilon that is too small, that is, we take a really small epsilon here, so if we make this our distance epsilon, we're in trouble because we cannot pick an interval small enough here that we aren't going to include these values and also these values way up here, which are going to be outside of that. They're not going to be within epsilon of our choice of the limit. And because there is at least one epsilon, probably lots of them, for which we cannot come up with a delta, so that all of the values of x in that region delta around c will give us values of y that are within epsilon of our proposed limit, then the limit does not exist. So I'm just going to say the limit does not exist. Okay, so that's the idea behind it. So I'm going to leave this one, and then I'm going to make a second video where we're going to work some actual examples of the kinds of problems that you're going to have to do on your homework and possibly on my test, not on the AP exam.